So here we are starting 11.1 with the notes for that section, and in this section we will talk about vectors in the plane. So we'll learn how to switch between the components of a vector and some of the characteristics of vectors like their magnitude or norm, the direction, etc. We will perform vector operations and interpret the results, so we will work algebraically but also geometrically. We will learn how to write vectors as linear combination of standard unit vectors, and we will apply what we've learned to word problems. So, a vector is a mathematical object characterized by magnitude and direction. There's two ways you can write a vector. When you handwrite it, you should always use this method, so V with an arrow on top. In the textbook, they don't have arrows, but they use bold letters to represent vectors. And it can be a little confusing sometimes, so handwriting it is much better to put an arrow. And in the pages that I hand out, pages that I wrote, or quizzes and tests, etc., it's always written with an arrow on top. I never use this bold method. So the magnitude is the length of the vector. You can also call it the norm of the vector. You can also just say the length if you want. And the way it's written is with this kind of double vertical lines, which look slightly like absolute values, and in a way that makes sense because the absolute value, you can also consider that to be the length between 0 and a certain number. How far is -8 from 0? It's at a distance of 8. So there is a little bit of a similarity between magnitude and absolute value. The direction of a vector is where it goes, and it will often be expressed by an angle from the x-axis. Now notice that the position of a vector is not relevant. Therefore, here's the same vector represented twice. It made me think that it's a little bit like when we use a mouse for a computer. It doesn't matter where the mouse is when you draw a line. It only matters how far you go and in what direction you go, and that'll show up on the screen. It didn't matter where you started with your mouse. When you sketch a vector, you can represent it with a variety of arrows, which we will call directed line segments, and we call the initial point or the tail where it starts, and the terminal point or the head where it ends. So these two directed line segments up here are equivalent since they represent the same vector. In the first example, we are asked to draw the directed line segment going from P to Q. It's done here, and then to draw another line segment representing the same vector, and the student Nick O chose to draw it here, but there's infinitely many other options. As long as you do 1 to the right and 4 up, it'll be the same vector. It doesn't have to start on the grid either, of course. To find the magnitude, we will apply the Pythagorean theorem. So in the example above, in order to find the magnitude of V, we will set up, so the vector here is the vector 1, 4, because from 2 to 3 there's 1, and from 1 to 5 there's 4. So for the magnitude, it's 1 squared plus 4 squared, and we take the square root of that. So the magnitude of V is root 17. A good place to always sketch vectors when you start is to put their initial point at the origin, and if you do that, then only the terminal point matters, and the terminal point, if it's v1, v2, then it corresponds to the vector v1, v2. Now here, when you put parentheses like that, it'll represent a point. If you put these kind of triangular parentheses, that is what we will use in multivariable to represent the components of vectors. And since I mentioned that, notice also that we call v1 and v2 the components of the vectors, but if we want to be really clear, when we talk about points, we say the coordinates of a point. However, it's never going to be dramatic if we, by mistake, even I do it often, I'm sure, if I say the coordinates of a vector or if I somehow say the components of a point, it's not gonna prevent anybody from understanding what we are talking about. But again, vectors with these triangular parentheses and then points with these regular parentheses. One more definition, a unit vector is a vector that has norm 1. So how can we find the component form and magnitude of a vector that starts at 3, 8 and ends at negative 2, 10? There's an important relationship that we need to always know. It's called the Schall relations. It's the fact that if you have a vector from A to B, written here vector AB, it's equal to OB minus OA, where O represents the origin point. So in this example, if I want to go from 3, 8 to negative 2, 10, what I can do is do minus 2 minus 3 and 10 minus 8. That represents OB minus OA. And this is the answer. The magnitude of this vector then is going to be, again using the Pythagorean theorem, 5 squared plus 2 squared square root, so root 29. Note here that we have another relation, AB plus BC equals AC. That is something we can see geometrically, and we will talk about that again in a few minutes. But if you have a vector going from A to B and then a vector going from B to C, we can put the initial point here at the terminal point of this vector, and we will see it corresponds to a vector that actually starts at A and ends at C. So algebraically, if you are given two vectors like here, you can add them component by component. So 2 plus 1 equals 3, and negative 1 plus 3 equals 2, which is why u plus v is the vector 3, 2. Negative v means negative 1 times v, so you multiply each component by negative 1. 3u, you multiply each component by 3. And if you have more than one operation, here it's 2 times u minus v, you can start by doing 2u, which is the vector 4, negative 2, and then you subtract 1, 3, and you get 3, negative 5. You can do exactly the same operations geometrically, and it's unfortunately on the next page, but if we sketch vectors u and v, well, I said that I would have vectors everywhere, and here I don't, but if you do u plus v, you can sketch u, and then the tail of the second vector, you just connect it to the head of the previous vector, so head to tail, so it's u plus v, and you look where you started and where you end. We started at the origin and we ended here, so in red you have the vector u plus v. In such a situation, we can notice, it's called a triangular inequality, that the norm of u plus v in red is bound to be less than or equal to the norm of v plus the norm of u. So there's always a detour. If we go somewhere else and come back, it's always going to be longer than to take the shortcut u plus v. The only time where it is equal, so it's greater or equal here, so the only time when these two sides would be equal is if u and v are parallel and going in the same direction. Then we would have norm of u plus v equals norm of u plus norm of v. Alright, continuing with the same operations from the previous page, if v is this vector, negative v is the vector in the opposite direction with same magnitude, and vector 3u is just u plus u plus u. So again, head to tail, adding 3 times vector u. So same direction, magnitude is tripled. Finally, last example, 2u minus v. We're just going to do u plus u, and then we add one of those negative v's that we found earlier, and we get 2u minus v. Note that if you have a vector u and a vector v, the vector u minus v, so let's say this is u and this is v. Oops, that didn't work. So vector v, vector u minus v is this vector. Let me just change colors. This is u minus v. So that might seem surprising. We can confirm that by thinking if I do v plus u minus v, I'm going to get vector u, as we saw earlier. So this is u minus v. So it goes from the head of v to the head of u. Okay, a bunch of properties of vectors which typically show us that vectors behave the way we expect them. You can add vectors in any order, so it's commutative, it's associative, etc. One thing that's quite important on this page to realize is this part here. You can see zeros twice, but they're actually very different zeros. One of them is the regular number 0. This one is bold, so it's actually a vector 0. So if you do 0 times a certain vector, you don't get the number 0, you get the vector 0. So a vector that doesn't go anywhere. But it still starts somewhere and ends in the same place. It's still a vector, it's not a number. So be careful. Here Nico added arrows everywhere it was appropriate, and you may want to consider to do the same until you're comfortable with recognizing when things are vectors or numbers. Numbers are also called scalars, by the way. So the magnitude of a vector, if you multiply a vector by a certain number, then the magnitude is also going to be multiplied by that value. And notice that we always take the absolute value of the factor c, because a magnitude is always a positive value. Finally, unit vectors. We mentioned earlier that a unit vector is a vector of length 1. So if you are given a vector v in the plane and you want to find a unit vector in the same direction, the trick is to find its magnitude and divide that vector by the magnitude. Okay, so if v has magnitude 5, now if I divide that by 5, I'm going to have a new vector which has magnitude 1. So here's a chance to practice that. How can we find a unit vector in the direction of v 5, negative 7? First we'll calculate the magnitude of v, which is 5 squared plus 7 squared, square root, and then we're just going to take v and divide by root 74. So there's two ways of writing that, and they're perfectly fine, both of them. You can write it as 5 over root 74, negative 7 over root 74, or you can realize that it's annoying to repeat that root 74 and you can just put the 1 over root 74 in front, which will be even more handy if we work in 3 or 4 dimensions, because you wouldn't have to write it 3 or 4 times. You could just, it looks like a factorization in a way. Okay, so there's two, among all the unit vectors, there are two that are particularly important in the plane, and we call them either I or J. So again, here this is a vector, and this is a vector. Instead of calling I or J, we will need to also get used to seeing the writing E1 and E2, because in many situations we're going to say vector E1 and vector E2 as well. The value of writing E1 and E2, of course, is that now we can just say En if there's n dimensions, whereas with letters we wouldn't know where to stop. But in 3 dimensions, it's also going to be quite usual to say that the standard unit vectors are I, J, and K. If we just work in n dimensions, we will always use E1, E2, E3, and so on until En. So we saw how to write vectors with components, but we can always express vectors as a linear combination of the standard unit vectors. Any vector in the plane is always a certain number of I plus a certain number of J, and it's super easy. the vector 5, negative 7 is 5i minus 7j's. So find the component of the vector that has magnitude 7 and makes an angle of pi over 6 with the positive x-axis. If you make a sketch, you will soon figure it out. But it's important to be very aware of the following relation. Whenever you have a vector, this is always true. The first component of the vector is always r times cosine theta, where r is the magnitude and theta is the angle with the x-axis. And the second component is r times sine theta. This is like, if you should understand this, and I'm sure you do understand it, but it should be at the forefront of your mind, because there are times where it's incredibly useful to just remember that. It shortcuts exercises quite a lot. Of course, the sketch here is excellent, and it illustrates this concept, but you should be aware of the concept immediately in all situations. So here's a little situation applied to real life. So two tugboats are pushing an ocean liner. As shown in the figure, each boat is exerting a force of 400 newtons. What is the resultant force on the ocean liner? So the thing is, it's not going to be 800, right? Because they are pushing at an angle and they are kind of pushing against each other vertically. So how do you do that? We add these two forces just like you would have done in Physics 1. And the result is that force 1 is 400 cosine of negative 20, 400 sine of negative 20. Force 2 is 400 cosine 20, 400 sine 20. And when we add these up using the calculator, we find that the resultant force is approximately 752, 0. So the vertical force cancel out, which is why the tugboat, which is why the ocean liner still moves horizontally. But the magnitude of the resultant force is 752 Newton, which seems very, very small. Okay, so that's it for 11.1. Thank you so much for listening. I'll see you soon.